All right, let's begin. Welcome, colleagues, to the lecture series on program effectiveness research. This is the second of 4 lectures that I will be delivering on program effectiveness research. Some of you will recall that lecture 1 discussed the logical underpinnings of this form of research, what it's trying to accomplish, how it differs from and contributes to other kinds of research in the field, and the central commitments that people in this line of work have about how to conduct research. Today, I want to build on that lecture by describing several kinds of research designs that are used in program effectiveness research. And along the way, I hope to discuss some of the strengths and weaknesses of each. Now, once again, I'd like to remind attendees that this lecture series is an introduction to program effectiveness research. As an introduction, I don't plan on discussing any of the topics in today's lecture in any detail, and would urge you to engage in additional study if you wish to have deeper learning than you get from today's overview. Remember also today that the emphasis is going to be on the ideas lining behind the choice of particular research designs, with much less, and some people might even say not enough, emphasis on statistical analysis of data that comes from the use of particular research designs. But my emphasis on ideas over statistics is because my goal is simply to point you to areas where you might need to engage in some deeper learning if you wish to conduct research independently. What I'm going to do today then is just sort of walk you through a variety of research designs. If you wish to use one of those research designs, I think you will be in an independent piece of research, you'll probably need to study a little more, and in particular, learn a little bit about the right statistics to use with that design. Now, to assist you in that and to deepen your learning and get you started, I once again will point attendees to some key papers that develop the topics I'm covering in today's lecture. Those additional references appear at slides at the end of the presentation. And as always, much of what I am talking about here is covered in a wonderful book by Shadish, Cook, and Campbell that I would recommend anyone who is embarking on a career in program effectiveness research begin their study with. Finally, a comment or two about the format for today. You know, the virtual format limits audience participation, but today at about 90 minutes in, when I am done presenting a lecture, I'm going to stop and open the floor for questions via the Zoom Q&A function. So if you wish to address a question to me during the first 90 minutes, hold it until that break point, and then use the Q&A function to post your questions to me. Then I would also ask you to hold comments to all in the Zoom chat box during the lecture and Q&A session, because it sort of pops up on my screen and clogs it a bit. So just if you could, you can chat between each other and to the hosts, but the comments to all, I would like you to try to resist until the end of the session, at which point audience members can see your thoughts. So let's start the lecture with some goals. The lecture, of course, is entitled Research Designs to Create Counterfactuals. And it's about how to implement the potential outcomes framework for causal inference through research design. And I'll say a little bit more and remind you what the potential outcomes framework is as we go on. But an initial set of goals for you is to understand that implementing the potential outcomes framework for causal inference in research involves creating counterfactuals that allow you to compare potential outcomes across treated and untreated cases. And today, the goal is to discuss several different research designs that can be used to create these kinds of counterfactuals for comparison. So at the end of the lecture, I hope you'll be able to understand how these various research designs do and do not meet the potential outcome framework's critical independence assumption, which is required for strong causal inference. Now, as I develop these topics, I also hope that you become accustomed to or learn a little bit more about how to reason about various threats to causal inference that arise when you're engaged in using different research designs, including research designs that do and do not use random assignment to treatment and control groups. And a final goal of today's lecture is to help think about the ways in which different research designs can be used at different stages of intervention program development. During early pilot stages, when design experiments are probably a good idea, as a program is preparing to move out of pilot sites through the conduct of what I call gateway studies, and which I discussed in my last lecture. And finally, to the point where the intervention program is scaling and we're interested in conducting rigorous impact studies. So to begin, let's review the last lecture and bridge to today. I'll do this very briefly. Recall that program effectiveness research is about deliberate efforts to make change. As a result, program effectiveness researchers most often deliberately manipulate some treatment, let's say A, to produce some outcome, let's say B. And program effectiveness researchers have adopted this, what's often called manipulationist approach to research, in order to avoid problems with correlational studies of naturally existing variation that I discussed in lecture 1. So you will recall that correlational studies cannot really clearly demonstrate first that A caused B, or confidently rule out the possibility that the correlation between A and B is spurious. The potential outcomes framework for causal inference does provide an alternative way to address the problems of correlational research, and it's become the preferred logical foundation for research on program effectiveness, both in the research community and increasingly in the policy community. So given its importance, let's review the potential outcomes framework very briefly. Recall, oh, well, that's sorry about that. Now, imagine in thinking about the potential outcomes that we're able to administer a treatment denoted T in a school, where that treatment seeks to improve the strength of, say, a school's professional learning community. So let T indicate that the school received such a treatment, and C that the school did not receive such a treatment. It is the control condition or the counterfactual condition for treatment. Now imagine that we could compare levels of student achievement at a given school when it did receive the treatment and when it didn't receive the treatment. So in this setup, we imagine that any given school I has two potential outcomes. YI, T if it's treated, that is its outcomes under treatment, and YIC, that is its outcomes if it is not treated. So in this setup, there are imagined counterfactuals. If we observe the school in the treatment condition, the imagined counterfactual is the potential outcome it would have gotten if not treated. If the school is in the control condition, the imagined counterfactual is the potential outcome it would have gotten if treated. And using this idea, we can define the causal effect tau of the treatment for a given school simply as the difference between its outcomes if treated minus its outcomes if not treated. So that's the basic setup for the potential outcomes model. Now, there is a fundamental problem with this model, and that is, as we go to estimate a treatment effect on some unit, we cannot observe that unit in both treated and untreated conditions at the same point in time. And so we have a missing data problem. At any given point in time, for any given unit we are studying, we can only observe its outcomes when it's being treated or when it's not being treated, but not both at the same time. But there is a way around this missing data problem. Instead of looking at the same unit in treated and untreated status at the same point in time, we can compare the outcomes for groups of units, some of which were treated and some of which were untreated. And as we're going to see today, sometimes those units treated and untreated are observations of the same case at different points in time when the unit is treated and when it is untreated. And sometimes the groups of units are actually different cases, some of which were treated and some of which were not treated. And under this procedure, we now define the treatment effect as an average treatment effect. That is, the expected value of outcomes for treated cases or treated units minus the expected value for cases that are untreated. So what is the link to today's lecture? The question for today is how to assign a study that allows us to observe these two different expected values, the expected value of the outcome under treatment and the expected value under the control condition. We also want to understand the bearing that different ways of creating observations under treatment and control conditions have for meeting the critical independence assumption of the potential outcomes framework, which is the independence assumption is that assignment to treatment is unassociated with any potential variable, which I will denote as X throughout this lecture, that might affect outcomes. Now, recall from last week's lecture that the most trustworthy way to assure that the independence assumption is met in some study is by random assignment of units participating in a study to either the treatment or control condition. That's because in expectation, random assignment to treatment and control assures that any X or set of X's that might affect the outcomes under study are distributed evenly and equally across treated and untreated units so that the comparison in outcomes across those units is simply representative of the causal effect of the treatment on the outcomes. Now, importantly, random assignment is not as difficult to achieve as many people assume, but many researchers don't use random assignment either because they have chosen to study a program that's already being implemented, it's too late for random assignment, or because they or those who they are studying think it is not feasible to use randomization in a particular setting. That brings us to the point of today's lecture, which is alternative strategies for creating treatment and control groups that don't involve random assignment. The key point of this lecture is to think about how these alternative designs assure or don't assure that treatment and control groups are equivalent on any of these X's, these variables that might affect outcomes, so that we feel comfortable that the independence assumption has been met. Now, there's the twist to my lecture, and that is the assumption that research designs can reasonably be expected to differ across phases of program effectiveness research. So what I'm going to do today is describe a series of research designs that researchers can use to create treatment and control groups at different stages of intervention development. So my argument involves seeing the development of intervention programs as unfolding in steps, where each step adds to our confidence that the program logic model is working as intended. And the steps in program development research are as follows. In pilot sites, or when you are just beginning to create an intervention, we engage in what might be called design experiments. As we've satisfied ourselves in the design experiment pilot stage that our program logic model is functioning as we expect, we move outside those pilot sites and engage in gateway studies. And these gateway studies can be thought of as studies that justify scaling up of the intervention beyond this group, this second group of sites, and early scaling. And then when a program has reached sufficient scale, it is time to conduct rigorous program impact studies. So what I'm going to do is show you that the designs that can be used at various stages of intervention development work in various ways to assure or not that the treatment and control groups are statistically equivalent on pretreatment covariates, these X's that I've been talking about, that might affect program outcomes. So I'm going to discuss a number of research designs today, and this is the guiding table for you to review at the end of today's lecture. But basically, I'm going to cover two dimensions of research design. The first, which is the top row of the table, is whether the design involves observing a single case or set of cases that are treated or not treated, or whether and so this is where the treated units will be observed in treated and untreated conditions so that each unit serves as its own counterfactual, or whether we're going to create different groups of treatment and control units, observing one in treatment and the other in control. And then second dimension, which are the columns of this table, is whether the data on the outcomes are gathered once after treatment, the post-only data collection, once before and after treatment, the pre-post design, or many times before and many times after, which I'm going to call time series data. So as I discuss it, my thinking is that some designs, which are shown here in the red ellipse and denoted by my little color scheme, some designs are very useful in the pilot and development stages of intervention development and can be used in what many developers call design experiments. Then, as you move into the need for gateway studies, we get another set of designs, which I'm going to discuss. And again, these designs are denoted in the red ellipse. And finally, as the intervention is scaling up and policymakers and practitioners wish information that is highly rigorous, I will discuss designs for random assignment, or what are known as randomized controlled field trials. So I'm not going to belabor this figure, but that's the general logic of my presentation, and you're welcome to study these slides a little bit afterwards, after the lecture. So let me launch into the various designs for the pilot stage of intervention. So let's begin with research on an intervention that's in very early stages of development and that involves a one-time only gathering of outcome data after the treatment has already begun. This is what I'm calling the post-test only cross-sectional study of treated units only. The design can be represented as you see it in the little boxes below, the white boxes, where T is the application of a treatment and O is an observation period. In a single site case study, a treatment T is applied to a single case, after which there's a single observation period for that case. And in a multi-site case study, a treatment T is applied to multiple cases, after which there's a single period of observation for these cases. Now, these cross-sectional treated-only subjects research designs are not well thought of in the literature on causal inference. And that's because from the standpoint of the potential outcomes framework, these cross-sectional case studies of treated-only units do not have a counterfactual built into the design. There is no observation of the units under untreated conditions in the post-only design. So there is no counterfactual. And for this reason, cross-sectional studies of treated units only can't be used to ascertain the impact of an intervention on either the implementation processes or on outcomes. But I would argue that these studies nevertheless can be useful to researchers in preparation for more rigorous studies. So a cross-sectional case study can be used if you want to develop measures of implementation processes and outcomes. For example, you can go into a case or cases where an intervention has occurred and observe closely to understand how your abstract concepts from theory in your logic model could be linked to concrete actions on the ground. That is, what you're looking for is real world instantiations of theoretical constructs. And then you use those to develop quantitative measures of an intervention's implementation processes or the student outcomes that you wish. So these are useful in preliminary work to develop measures. And multi-site case studies are better than single-site case studies because in a multi-site case study, you can begin to understand the range of variation that you might observe both in implementation and in outcomes. And you can use that range in turn to begin to think about benchmarks for assessing and measuring how the intervention process proceeds over time. So you cannot use these studies, this design to study the impact of the program on outcomes because it lacks a counterfactual, but you can use it for measures, development, and other things. So how do we get counterfactuals? Well, one way to do it is to add time points in the treated only case study. And in particular, add time points under which we observe the same case in both treated and untreated condition. So that the design here is shown again in the white boxes. Notice that we observe the case in untreated condition. We apply the treatment T and then observe the case again after the treatment is applied. And in the multi-site case study, it's the same design, just with multiple cases. Now, what's interesting about this design is each case is now its own counterfactual. And because we have this counterfactual, we can now actually calculate tau average as the value of the outcome under treatment minus the value of the outcome in the control condition prior to treatment. So now we have each unit serving as its own counterfactual. But this design has certain limitations which are important to understand, and you need to take extreme care when you interpret findings from these studies. So here are the main threats to the inference of a causal program effect on outcomes from such a design. For one, any difference that you observe in outcomes from before to after the intervention could be due to a lot of factors other than application of the treatment. It could be due to maturation. That is, in many instances, we naturally expect positive changes in the outcomes as a normal product of the passage of time, maturation, aging, and so on. It could be the case as well that history accounts for changes in the intervention. That is, something is happening in the outside environment that could have driven the change in outcomes from pre to post treatment that was not the intervention. It could be measurement reactivity. There is a tendency, for example, if we give achievement tests to students, that the second time around, if they take the same test twice, they're going to score higher. So that's measurement reactivity. And many times people who respond to all kinds of surveys will react differently the second time they take the survey than the first time. And finally, there could be changes in sample composition, and you look only at a part of the whole sample. And the problem here is what I will call selective attrition or selective attrition in this case. That is, suppose we apply the treatment, suppose we observe a set of cases, apply a treatment, and then observe the cases the second time around, but after post-treatment, some of the cases have left. For example, individuals might leave an intervention, might leave your study because they don't like the intervention and can't do it. So now we're left only with the data on people who can do the intervention well and like it. And that could be the explanation for why we get this difference in treated and untreated. So let's just go through this. The key assumptions required for pre-post designs to lead to valid causal inferences are, first of all, that the characteristics of individuals or samples of individuals being observed do not change over time. That's called the unit homogeneity assumption. And that the context in which we observe remains constant except for application of treatment. If you can rule out maturation in history and reactivity and changes in sample composition, then it is possible that these pre-test, post-test designs are going to yield a decent estimate of program effect. But an even better design for creating counterfactuals in treated-only studies is to add multiple pre and post-treatment observation periods. So here in the white boxes, you see what that looks like. We observe several times prior to the application of the treatment. We apply the treatment, and then we observe several times after treatment application. And once again, we can calculate the treatment effect as simply the difference in average outcomes after treatment minus average outcomes before treatment, where each case is thought to be its own counterfactual. Now, there are limitations to this design with treated subjects only. For valid causal inference, we once again have to assume that the characteristics of the units themselves didn't change over time, except as a result of treatment. And we have to assume that the context remains constant, except for the application of treatment. And in cases where we have multiple pre and post tests, we can at least begin to subject these assumptions to some empirical disconfirmation. For example, if there are maturation threats, that is, positive changes in outcomes occur as people age or as time passes, you would observe that maturation in both the pre-test phase and the post-test phase. And so you could take maturation into account when you estimated the treatment effect. If there's measurement reactivity, that is a tendency for individuals to score higher on measures if they're responding repeatedly to the same instrument, once again, we should observe those in both the pre-test and the post-test periods, and we can take that into account when we estimate the treatment effect. History threats, similarly, could be observed in both the pre and post-test periods. And so, one assumes that over a short interval, the history that's affecting outcomes is observable in both pre and post periods. And so, in some sense, history is taken care of. There is always the possibility that some historical event occurred contemporaneously with application of the treatment and caused outcomes to change. And so, but that should be working on both groups. However, the changes in sample composition, and particularly differential changes in sample composition, can also occur, and that cannot be controlled in this design, or for that matter, almost any design that we're going to discuss. So studies that have these multiple pre and post data collection periods are often called, quote, interrupted time series designs. And so here's an example of how such data might look. The graph on the left presents that, where the interruption in the time series is that red line where the treatment is applied. It's a time series because we have multiple observation points denoted by those gray dots. We have an interruption, and we're studying pre and post trends in the outcome. So if you look at the graph on the left there, you see there's no time trend before the intervention, but a positive time trend after the intervention. And again, recall that we're studying only treated subjects. So the lack of a time trend before the intervention helps rule out threats to inference of program effects like maturation or history or measurement reactivity. That line is flat. There doesn't appear to be some historical trend. People don't appear to be naturally changing over time in any positive or negative direction, and they're not really reacting to the measures in any observable way. But if those threats were present, we would see them in the pre-intervention period. So using these data, and then you notice how there's a sort of a curve going upward. If we look at these data and use them to calculate tau average as I have defined it, the effect would be high. The effect would be positive and looks promising. However, there's still some threats that you have to be cognizant of. One is that some event occurred simultaneously with the intervention that caused this observed change. And you could have had attrition in your sample so that when you come to look at complete data only on the people left in the study, the people who left were those who would be least subject to benefit from the intervention, leaving only those people who are subject to benefit. That's the sample attrition problem. It's present in just about any form of study. Now, that seems all easy, but here's excuse me, two other examples of interrupted time series data where the inference is not as easy as it was in the last graph. So let's begin with the graph on the left. And in this graph, notice there's a positive time trend before the intervention. And that could be due to maturation or history or measurement reactivity. And notice after the intervention, that time trend continues. Now, the thing of this is, if you calculated the simple difference between pre and post, you would conclude that there's a positive causal effect because the outcomes are indeed higher post-intervention than they were pre-intervention. But that could well be because there's a time trend in the data due to maturation or history or measurement reactivity. So again, you may find a tau average, but the threats of history, maturation, or measurement reactivity are present in this particular set of data. Now let's shift over to the right-hand side and notice, once again, we see this kind of positive time trend both before and after the intervention. And again, this could be due to maturation or history or measurement reactivity or any number of things, but that trend is continuing. But notice the breakpoint at the point of intervention. There's a uniform addition to outcomes in the post-treatment period. And it's this uniform increase apart from the trend in the outcomes that suggests that there is in fact a treatment effect going on. So again, sample attrition and history effects are possible. That is, somehow something happened contemporaneously that created this uniform increase, or somehow a certain set of people who don't react well left, and that created this increase. But again, you see that it requires some judgment when looking at interrupted time series for treatment only. It requires some judgment above a simple time trend. It requires the addition of a uniform jump in outcomes for you to conclude, in the presence of a time trend, that there are program effects. Now, Uh, those designs I think are very useful in the early exploratory stages. Sometimes even without using complex statistics, you can observe the data and the effects are big enough that they're observable. But there are additional treatment-only time series designs that I think are also worth thinking about. And these are designs which I find particularly useful as tests of a logic model, as that logic model is being developed for the first time in an intervention program in its pilot sites. Now, I've borrowed these design concepts from the literature on single subject research designs, which is a very interesting and not much appealed to literature in the general program effectiveness research, but it is a set of research designs which are often used when studying samples of children with disabilities or rare cases. And so I want to describe some potential designs from this literature that I think are very useful to use during program development. And once again, these can be used with only treated cases where we observe the same case with and without treatment, using each case as its own counterfactuals. And I'm going to talk about two of these designs, the ABA or switching or reversal designs and the multiple baseline design. So let's start with a switching design. This design turns an intervention on and off for the same subject or group of subjects. So you'll see that in the design in the graph on the left, A is a no treatment condition, B is a treatment condition, and A is a no treatment condition. So we have the intervention is off, then it's on, then it's off. So when you have an intervention that you hope produces learning on the part of recipients, or when you plan to provide an intervention and then withdraw those services at some point, this ABA design allows you to see if post-intervention outcomes persist after you withdraw the intervention services. And of course, there's multiple possibilities here. So for example, that little star 1 in the third panel of the figure shows that we have low outcomes prior to treatment. The outcomes go up during treatment. And once we withdraw treatment, the outcomes persist at a higher level than they did in the first baseline. And that suggests learning and persistence of the intervention. On the other hand, what you see in the little star 2 is a decline in outcomes once service is withdrawn to the earlier baseline, and that suggests that the intervention does not have persisting effects. And you may need to fiddle with your design if you hope to achieve persisting effects. The next one is what's called a multiple baseline study, and it's particularly useful for studying interventions which have multiple components, and your design strategy is to phase the components of the intervention in over time. And so imagine in this case, let's go back to my usual example of trying to intervene on professional learning communities in schools. Supposing we're trying to change 3 dimensions of professional learning communities: how frequently they meet, the kinds of discourse practices that they use while they're meeting, and whether or not they discuss students' work. Now, suppose we introduce those services in a particular order, and that order is shown by the horizontal line. So first, in the graph to the left, first we provide services that are going to increase meeting frequency. Then we provide services to increase discourse practices. And then we, a little later in time, we intervene to get these communities to discuss student work. The point of a multiple baseline study is that throughout the course of the study, we are measuring each outcome: how frequently, the groups are meeting, whether they're using the discourse practices that we're trying to encourage, and whether they're talking about student work. And what you see in the graph at the left is a successful case of a kind of sequential intervention. Notice at the very top panel, there's low meeting frequency until you intervene, and then meeting frequency goes up. But notice that the other measures remain unchanged. All you've changed is meeting frequency. Then at a certain time period between 0.7 and 8, you introduce an intervention for discourse practices. And what you notice is that now people begin to engage after that intervention in the kinds of discourse practices you want, and meeting frequency is maintained. And then a little later, you try to get people to talk about student work. And what you see is that they do begin to talk about student work. They don't decline using the discourse practices, and meeting frequency is stable. So it's an interesting design because it shows the sequence of effects, but it also is an interesting design because it's ruling out various threats like history and maturation and measurement reactivity as potential alternative explanations for the treatment effect. So notice, for example, if history and maturation or measurement reactivity were going on, we would observe that in each panel, but we don't. We only observe an outcome going up after the intervention is applied. And then notice that the intervention outcomes seem to persist over time. So this is a very interesting design. I think it's one that's really well worth using, even without complex statistics at the early points of intervention, to develop a logic model. So let me summarize the treatment group only time series studies that I've been talking about. When we measure outcomes at multiple time points before and after treatment, we create a counterfactual in which each unit serves as its own control. And because that's going on, we can calculate tau average within the potential framework, within the potential outcomes framework. We define E, the expected value of Y given treatment, as the average outcome for the units observed after treatment. We define the expected value of the outcome in the control condition as the average of outcomes of units before treatment. And so we can now calculate the tau average that is discussed in the potential outcomes framework. Now, it is my view, and I think most people's view, that interrupted time series designs, that is, designs that have multiple pre and post observations, are more useful than post-only or simple pre-post designs for studying treated-only units. In the time series designs, the observation of time trends prior to the intervention can help you, at least in part, rule out threats to inference such as maturation and measurement reactivity, because if you don't see them in the pretest, then there's little reason to expect that that's what's going on in the post-test. On the other hand, observation of trends in the data prior to intervention can't definitively rule out those threats. There could be the case that the historical change occurred right at the same time as your intervention occurred, and it could be that there's this kind of selective post-treatment attrition. But the beauty of doing small exploratory studies using these designs is that you can use qualitative or other additional data that you're familiar with your context, and so your familiarity with the context can help you address the likelihood that these latter forms of threat to causal inference are present. Now, if you add these switching and baseline designs to the time series, you're getting even more useful studies, especially for the development of interventions. They're going to provide those kind of threats to inference that arise because of maturation and measurement reactivity. But again, they can't really rule out threats to inference due to history or selective attrition. But the main reason to use these designs, especially switching designs, is to test for learning or persistence effects after intervention services are withdrawn. And multiple baseline studies will help you examine what happens when multiple components of a complex intervention are implemented sequentially in a intervention development. So now let's move away from designs in which the same unit serves as its own counterfactual because we observe it in treated and untreated conditions, to designs that create treatment and control groups composed of separate units. So now we observe one group of units under a treatment condition and another separate group of units under a control condition. So, you know, treated only designs that we have discussed have these maturation and history threats. But if we add these separate control groups into a study, we help control for maturation in history, since we assume that any maturation or history is going to affect the treatment and control groups similarly, especially if these naturally formed groups are roughly similar in maturity level and are in similar historical contexts. So the treated only ones seem strong because if you assume unit homogeneity, you know that the treatment group and the control group were exactly alike on pre-treatment covariates. They're the same people. But you have these threats to history and maturity. Now, when we go to a separate treatment and control group design, we sort of are controlling for history and maturity because we have a control group to observe the trends in. The problem with using separate control groups is it introduces the strong possibility that the two groups are actually not alike on a set of pre-treatment covariates that affect outcomes, so that these pre-treatment X's, the X's that I've been talking about, aren't distributed evenly across groups, and that would violate the independence assumption. So the point now, when we discuss these separate treatment and control group studies, is to think very carefully about how researchers go about trying to assure their audience that the control group is like the treatment group on pre-treatment covariates. So that's the main idea here. Again, these designs have these multiple time points. We have the post-only comparison, where, you know, in the post-only comparison, both the treatment and control group are experiencing the same history and maturation processes, but again, they could be very different on pre-treatment covariates that affect outcomes. So that's the major threat. The observation of treatment and control both prior to and after treatment is another design, the simple pre-post design. And again, in this design, you know, you can make a judgment about whether they're in the same context and of similar maturity levels, and that would rule out maturity threats. But again, we have this problem of non-equivalence of treatment and control on other pre-treatment covariates that might affect outcomes. And then we can do a comparative interrupted time series in which we are taking time series data on both treated and control units. And again, you know, if they're similar in maturity and context, then we're sort of controlling for those factors. But non-equivalence of treatment and control on these pre-treatment covariates is the major threat to inference. Okay, so the problem is, how do we address this threat that the treatment group and the control group are not alike on pre-treatment covariates that might affect outcomes? Or how do we address the potential for a violation of the independence assumption of the potential outcomes framework? On the next slide that I'm going to show you, I discussed 3 approaches to dealing with the problem of non-equivalent groups. One is instrumental variables analysis. I am not going to talk about that today. I have a place where you can go to read about it. It's commonly used in econometrics, but just for purposes of today, I'm not going to discuss it. What I'm going to discuss are 2 other approaches. One is called difference-indifference analysis, and the other is called statistical matching. So let's discuss the difference-indifference analysis and overview. So the difference-indifference approach uses interrupted, or in this case, comparative interrupted time series. For both the treatment and control, we have multiple observations during the pre-treatment time period and the post-treatment time period. And we assume that if the time trend for the treatment and control is exactly the same during the pre-treatment time period, then we assume that all pre-treatment covariates affecting time trends during the post-treatment period are equivalent across groups. Now that's a strong assumption, and it is worth remembering that that is the assumption. Now, if in fact, when we observe the data initially, the time trends are not the same across treatment and control in the pre-treatment period, it's time to dump this approach. But even if one finds no difference in time trends in the pre-treatment period between treatment and control, it's not a guarantee that the assumptions of this model have been met. So that I'm going to show you that in a little bit more detail here in a minute. Then the overview of matching is this is an attempt to use existing data on pre-treatment covariates for the subjects in a study to equate the 2 samples on these covariates. And there are 3 ways of doing it: exact matching, distance matching, and propensity score stratification. But here is the key assumption. All these methods of statistical matching assume that matching controls for all relevant pre-treatment covariates that affect outcomes. And that leads matching to rely on what is called the conditional independence assumption. We have matched on some observed X's. We assume that conditional on the matching of treatment and control on those X's, assignment to treatment or control is now unrelated to other pre-treatment covariates that we did not observe, but that might affect outcomes. Now, we can examine the extent to which matching has in fact equated the treatment and control groups on pre-treatment X's, but we actually can never be sure that treatment and control groups are matched on all unmeasured pre-treatment covariates, and that's the main flaw with the matching design. So let's look at these 2 designs in a little bit more detail. The first is the difference-indifference approach to analyzing comparative interrupted time series. So here's a closer look at the difference-indifference approach. This is a very complex graph, but it illustrates what you might find in complex form in such a study. So imagine now that we have data points, many data points before an intervention is applied. The blue line happens and we have a bunch of data points after the intervention has been applied. And we have 2 groups, a treatment group in red and a control group in green. Now notice that during the entire pre-treatment time period, the left side of that panel, the data show that outcomes for the 2 groups are changing at the same rate. And notice also that there's a constant difference in outcomes at pre-treatment, in this case that favors the treatment group, and is denoted in the slide, in the graph, as the constant difference in outcomes. So the assumption is that this initial difference that we observe on the left-hand panel captures the effects of all pre-treatment covariates on both status and change in the outcomes. And if you make that assumption, then we would expect that if the treatment had no effect at the post-observation period, there wouldn't be any difference in outcomes among treatment and control other than the constant difference that we observed at the first time point. And that's denoted by this dotted line called the unobserved counterfactual outcome trend for the intervention group. If, as in the graph, there's a larger difference in outcomes at post-treatment, then we assume that this larger difference must be due to the effect of the treatment on outcomes and only that. But we do it by assumption because we're assuming that all other factors affecting rate of change are constant over time. Now, I won't get into the statistics of this. It's easy enough to Google to figure out the statistics involved in making the estimate of the intervention effect from data like this. The point I am emphasizing are the assumptions that underlie the model. So for this difference in difference designed to yield a valid causal inference, the investigator needs to demonstrate certain things. First, as always, that there's no differential attrition across treatment and control groups over the course of the study, so that it's attrition, not the causal effect. That's true in any design. That the treatment and control units didn't experience different types of context changes across time point. That's the kind of constant context and equal context for both groups. The most important assumption is that time trends are demonstrably equivalent in treatment and control in the observation period, because if they're equivalent time trends in the pre-observation period, we've assumed now that we have a handle on all the pre-treatment covariates that are affecting outcomes. And then we assume that the naturally occurring allocation to treatment was independent of any of these pre-treatment X's. That is, somehow we've just controlled those away by looking at the trend lines. Now, the first three assumptions, that there's no differential attrition, that they didn't experience different context, that the trend lines are demonstrably equivalent, those are all subject to inspection and verification. But the last assumption, that in fact we have assured that allocation to treatment is independent of any pre-treatment covariates that might affect outcomes, we can't really verify that because we don't have any knowledge of all the pre-treatment covariates, and that's the chief threat to inference in this design. Now let's take a closer look at matching processes and matching units in treatment and control groups. So matching is an attempt to make sure that the treatment and control groups are equated on a wide range of pre-treatment covariates that we have good reason to think affect outcomes. And we use that to meet the independence assumption of the potential outcomes framework. That's the requirement that assignment to treatment is independent of pre-treatment covariates that affect outcomes. Now, this is important. Matching only partly meets the independence assumption. It assumes what's called conditional independence. The assumption under matching is that given a set of observed pre-treatment covariates on which the treatment and control group are matched, assignment to treatment is independent of other pre-treatment covariates that affect outcomes. But this, just like that the equal growth rates has controlled for pre-treatment covariates, the notion that matching actually gets rid of other than observed pre-treatment covariates as a nuisance variable is a very strong assumption and mostly untestable, and it's the main flaw in the matching procedure. But nevertheless, let's talk about some procedures. So I'm going to talk about 3 ways that people use to match treatment and control groups on a set of covariates that they have measured at a pre-treatment time point. The first is exact matching. The second is distance matching on a set of covariates, and the third is propensity score stratification. And each process begins in exactly the same way. Let's just assume you're observing a set of schools that are under treatment, and there's another set of schools out there that aren't being treated, but you can get data on those sites. Then you collect or locate data on all those sites that includes measures of pre-treatment covariates that theory and prior research suggest could affect the outcomes of your study. You make sure that these are taken at pre-treatment time points, and then you match each case in the treatment group to one or more cases in this potential control group on the measures you've collected. Crucially, discarding from analysis any treatment group cases for which you can't find a suitable match because they won't have a suitable counterfactual. Well, a question people often ask me is, where do I find these control group cases? So it's my view, and I think the view of a lot of people who do this kind of work, that the best potential matches are untreated units located in the same context or context as your treatment group cases, because that'll help control for history threats, since both the treated and untreated units in your study will be in the same general context. So it's important not to choose a treatment group in one area and a control group from an entirely separate area, because they may be having different histories. So the best chance then you have of finding suitable matches is also to have a very large potential control group available for matching, because if you have fewer potential matches, you might not find suitable matches for all your treatment group cases, and therefore you'll have to discard cases, and now you start losing sample size. So you want to have a fairly large potential control group. And then because of that, many people use administrative data sets that include measures of things like the kids' prior achievement and student body ethnic and socioeconomic composition or teacher qualification. Those are often used in matching studies because these administrative data sets, because they have many potential control variables, or many potential control units, and existing measures of things we know affect student performance. So how do I figure out which pre-treatment covariates to measure when I'm doing matching? The advice is to rely extensively on existing theory and prior research to enumerate which pre-treatment covariates potentially affect outcomes. So make a list from theory and prior research of the things you ought to measure because they're known to affect achievement or whatever the outcome is. And so, if the outcome is student achievement, well, then we know from theory and research that we ought to control for the socioeconomic and ethnic composition of schools. And if it's a post-test only, or even a pre-post, we ought to control for absolute levels of achievement in the schools before the intervention, even time trends, although you don't need to do that if you're engaged in the interrupted time series. Now, it's a little more, supposing we're interested in implementation outcomes, it's a little more difficult to imagine the relevant pre-treatment covariates for that kind of study, but might be things like school size or teacher qualifications or teacher experience. So the point is, you appeal to theory and prior research to enumerate the pre-treatment covariates that you should be measuring. And then you find as many of these as you can, and you measure the potential controls and the treatment group on these units. And now supposing you have that data and you have it on a large sample of possible controls. In the exact matching procedure, what you do is find units, let's say in our case schools, that are exactly like each treatment school on each of the covariates you're including in your matching process. And any cases of control cases which match exactly to treatment cases are included in your study. Now, exact matching sounds great, but it's often difficult. It's difficult when there is a lot of pre-treatment covariates on which you need to exactly match. I mean, the more things that need to be exactly matched, the harder it is to find exact matches. It's hard to do exact matching when the covariates are continuous variables. I mean, you know, the two schools to be exactly matched on some variable that varies from 0 to 100 have to have 50, two 50s. I have to find those. And if there are only a small number of potential control units available, that makes it hard to match. So exact matching is actually difficult under a lot of circumstances that you would normally face. For that reason, many people don't use exact matching. They search instead for a set of potential schools that are most like the schools in the treatment group. And the usual way this is done is through something called the Mahalanobis distance algorithm. But the idea here is if we have a lot of variables, a multivariate data set, that multivariate data has a central mean known as a centroid, which is the point where the means of all the pretreatment covariates intersect. And in the Mahalanobis distance matching, you calculate the distance of each case from this centroid, and then you match the treatment and control schools so that they have the same or roughly the same distance from that centroid. So you can match the distances from the centroid exactly. You can match it within a certain caliber, you know, caliper matching, or there is a method that you can use to match that minimizes the total difference among treatment and control cases in the sample as a whole. That's known as optimal matching. And by the way, you can match more than one control case to each treatment case if you want. Although when you do that, you should make sure that no control case is matched to more than one treatment case. And once again, if you don't find a good match, you discard the treatment case for which a suitable match can't be found from the analysis. So that's the distance measure method. And the final way is propensity score matching. Now, a propensity score is the probability that a given unit will be assigned to a treatment, to the treatment condition, given a set of pretreatment covariates. So in practice, we have a data set. It includes our treatment schools and the potential controls. And we calculate the probability that any unit in this data set is going to be assigned to the control group using a logistic regression in which the observed pretreatment variables for all cases predict whether or not that case is in the treatment group or the control group. And that predicted value plus the residuals turns out to be a probability, and it's called the propensity score. Now, the beauty of a propensity score is that units that have the same score will also be roughly at the same centroid in the multivariate space and hence matched, but also treatment or control status will actually be independent of, that is, unassociated with, the pretreatment covariates used in matching. And so this meets the conditional independence assumption. And so again, you can use these propensity scores to form exact matches, or you can sort of use optimal matching, but a very common procedure is to create 5 or more strata, that is ranges of propensity scores, and then compare outcomes within these strata. That's called propensity score stratification. Now, whenever you do matching, it's very important to evaluate the quality of those matches, except perhaps for exact matching. So a properly matched sample has 3 features to it. It doesn't differ on the means for all pretreatment covariates. It doesn't differ on the variances or ratios of variances of the pretreatment covariates, and the distribution on those pretreatment covariates is symmetric across the groups. If you are doing matching in your study, you must investigate whether these conditions obtain prior to doing your outcome analysis, and you should demonstrate it to readers that you have appropriately matched and met the assumptions of matching. And sometimes it takes a while to get good matches. It is permissible in this literature to use different matching techniques or to reiterate, go through iterations until you get good matches. It's okay to do that because the point is to get these good matches and meet the assumptions of matching. Now, again, although matching helps assure that treatment and control groups are matched on observed covariates, it doesn't assure that these groups are matched on unobserved pretreatment covariates, so that even after matching, there could still be a failure of the independence assumption. Now, there are various ways that I discuss, but in the interest for helping readers see the extent to which you may or may not have violated that, or showing them the consequences of potential violation of that, that's discussed in the 2 bullets below. But in the interest of time, I'm going to move on. And so let's review. Matching assures that the 2 samples are matched statistically on pretreatment covariates that we think affect outcomes. And in that sense, I think matching designs are better than designs that have unmatched or non-equivalent treatment and control groups. They are troublesome to do because they require that you have data on pretreatment covariates, and that might or might not be available. And if data are available, it might not include the correct set of covariates. And so, that's a problem. It's possible that some units won't have matches and have to be discarded, and that's troublesome. And finally, matching is not a substitute for random assignment, and random assignment is definitely preferred over matching. Once again, all of the designs with respect to when data are collected can be used in matching. And I'll let you examine this in the interest of time. I'll let you examine this table in more detail. But the point is, this table shows you in a particular design which threats are ruled out and which threats aren't. But the main point is that you can never rule out the possibility that there are some unobserved pretreatment covariates that are affecting outcomes. And so you may not have properly identified tau average. So we've gone through treated only subjects, treatment and control groups that use either the difference in difference approach or matching. Now we come to random assignment. So the designs that I talked about before random assignment are useful in exploratory stages of intervention development, but the gold standard for assessing a treatment effect in program effectiveness research remains the randomized field trial, where units are assigned to treatment and control randomly. And that is because that is the strongest guarantee and an expectation it will guarantee that there are no unobserved covariates that are affecting the outcome and also associated with assignment to treatment. So let me talk for a few minutes about how to conduct a random assignment study. The first step is to identify the units that you want to use in the study and that will be randomly assigned. The next step is to randomly assign the units. The next step is to begin treatment in the treatment schools, withholding treatment in the control group. And the final step is to estimate the treatment effect. So let's talk about how do you go about identifying the units to be studied. So random assignment studies are prized for what is often called in the program effectiveness literature and in research design literature generally, internal validity. Internal validity is the assurance that tau average, the treatment effect, has been properly identified, that is unbiased and of the right size. But random assignment studies also confront what's known as external validity, as do all of the designs discussed in today's literature. External validity refers to the population of units to which one the findings from the randomized study generalize. And so the concern with external validity should lead researchers to carefully consider what units they want to include in their study. So there are two important concerns when you select sites for random assignment. One is, does the study want to generalize to units that provide a best case scenario for implementation? Or are you studying a set of units that might take up the treatment under natural circumstances? So if the former is the case, we often call that an efficacy trial. It's a trial, a randomized controlled trial with using a set of sites which are predisposed to probably do well with the intervention. If the latter is the case, that is, you're just taking a general sample of schools, that's called an effectiveness trial. The second thing that you want to think about when you think about picking schools for a random assignment trial is, do you wish to generalize the results of this study to the entire population of units? For example, are we trying to generalize in a randomized field trial to all kinds of schools? Or are we trying to generalize only to a certain subpopulation? For example, schools that are serving high percentages of poor and ethnic minority students. So that's a second concern. Importantly, before you do a randomized field trial, you should have identified the relevant population you wish to generalize to. And then what you do is you create some kind of a sampling frame for that population, a set of units from which you are going to select study units. Then you choose units from that frame for possible study. You can choose those units randomly or probability. That is, it can be a random or probability sample of the frame, or it could be just a convenience sample. And in most cases, randomized controlled field trials are using convenience samples of a predefined population. Now, you can also block or stratify or match prior to selection. And so you'd block, for example, and I recommend that you do this, you sort of block by jurisdiction to control for history. You can stratify on the basis of various pretreatment characteristics to assure you get a balance of types of schools. And you can match units prior to recruitment into this study, so that you're, picking replicates. You say these groups of schools are alike. Let's try to recruit schools from that matched group. So once the units have been selected for recruitment and you've recruited them, you recruit them under the condition that they accept random assignment. You recruit schools under the assumption they do not know if they'll be in treatment or control. They have to accept random assignment. And only after recruitment occurs are the units randomly assigned to treatment and control. If you blocked, you randomly assign within blocks. If you stratified, you randomly assign within strata. And if you matched, you randomly assign within matched groups. Once the units have been randomly assigned, you should check two things. First of all, that the groups are in fact equivalent on a bunch of important pretreatment covariates. You do the same kind of analysis you would do in a matching study, just to make sure that randomization worked. And, randomization only works in expectation. There can be failures to randomization. And then you also want to check the difference between the study sample and the actual relevant population that you were trying to sample from. How different is your study sample from the sample you're trying to generalize to? And I won't talk in the interests of moving on anymore about that. A couple of questions, a couple of comments about the types of designs that you can use in random assignment studies. Again, you can use post-only, pre-post, and comparative interrupted time series. I will say one thing. The post-only design, where you apply treatment and observe outcomes afterwards, often has a bad name. But in a random assignment study, you have assured that the treatment and control groups are similar on all kinds of observed and unobserved pre-treatment covariates, and there's really no need to statistically control for any kinds of covariates when you estimate tau. And because of that, these post-only designs are actually quite good, except for the potential of differential attrition. Now, you can add a pretest of the outcome, that pre-post, into a randomized controlled field trial. It's not needed, but it does improve statistical precision for estimation of tau average. And that's useful because it improves power, and you can get away with a smaller sample size. So that's the reason to use a pre-post design. And the advantage of using many post time periods in the comparative interrupted time series is that it gives the program effect some time to emerge. So in that post only, quickly after after treatment, we may not have given the treatment enough time to take hold. Whereas when we observe many times post treatment, we are giving the treatment some time to unfold and take hold. All right, so let me then summarize the gist of today's lecture. And it was long and complex. I have discussed today a variety of research designs that get used in program effectiveness research. The first set of designs that I talked about were case studies of one or more treated units only, and that measured only post-treatment outcomes for those units. And I argued that this type of treatment group only, post-test only study doesn't even create a counterfactual, and therefore can't be used to study program impact on outcomes. But it could be useful to develop measures of program implementation and outcome as you move forward. The second group of study designs I described were also studies of treated units only, but they created counterfactuals by studying each unit before and after it was exposed to treatment. So in these units, or in these studies, each unit is serving as its own control. Now, I argued, and this is an important assumption, that the treated units only studies rely on the unit homogeneity assumption to argue that the units were exactly same in pre-treatment and post-treatment periods, except for any effects for exposure to treatment. It's a strong assumption. You need to sort of be sure that that assumption holds for the pre-post comparison to be logical and good. I argued that the least useful of these pre-post is the simple pre-post design, because it provides little information to rule out threats such as history and maturation and measurement reactivity, that it's much better in treated only studies to do interrupted time series designs where you observe the outcome many times before and many times after, because that helps you examine the extent to which maturation and measurement activity and reactivity and so on are going on. I also discussed a couple of other designs that involve treated only subjects with time series data, the switching and multiple baseline studies. I find these really interesting and very useful as ways of thinking about doing design experiments. But again, the key thing is to assure yourself that the treatment and control groups are reasonably equivalent, or they're reasonably worth comparing. And then I moved to discussion of designs that add a control group. And so, whereas these studies of treated units only use each unit as its own control under the unit homogeneity assumption, the separate treatment and control groups face this problem of non-equivalent groups where they can differ on pre-treatment outcomes. And so the question is, how do I address that problem in research design? And I discussed the difference in difference approach and the matched treatment and control group approaches. I showed various ways that you can check whether assumptions about treatment and control group equivalence hold in both the difference in difference design and in matching designs. But I argued that both designs cannot definitively assure you that the treatment and control groups are equivalent on all pre-treatment covariates. Some, especially matching, shows you that they're equivalent on observed pre-treatment covariates, but not all pre-treatment covariates. And as a result, these designs are always subject to some omitted variables bias that would make your effect size be biased, your effect size estimate be biased. And so the solution, I argued, the definitive solution, is to randomly assign units to treatment and control groups, because that assures an expectation that the two groups indeed are the same on any possible pre-treatment covariates that might affect outcomes, although that needs to be checked. And then the final argument I made today was that different designs are appropriate to different stages. So these treated subjects only designs that I described, I find very useful for program development, during the program development stage. There are some versions of these designs, but moving towards quasi-experiments, that I think, although they have a bad reputation in some circles, they are at least useful to ascertain whether a particular program is a good candidate for scaling. If you can't show an effect in a quasi-experiment, then there's really little money to really little reason to spend a lot of money conducting an extremely rigorous and high cost randomized controlled trial. But if you meet that gateway, that is on a set of numerous quasi-experimental studies, you've shown that you have an effect, and you'd like to have that program tested for whether it's worth scaling up, then it's time to do these randomized controlled field trials, because they provide strong evidence that a program is worth scaling up. So I'm going to conclude with the lecture period and move to the question period now. So I can see that I have 11 questions so far, and I'm going to take those questions now. If you don't mind, if you have a question, please post it in the Q&A. So the first question is how to do program effectiveness research on the new normal learning approach with struggles in learning resources and limited data and information. I'm not sure if this question is asking about how to do program effectiveness research where we're in a world of COVID and things have sort of shifted online and it's difficult to access participants and so on. And so I would agree that it has become, in the current COVID world, extremely difficult to do the usual kinds of program effectiveness research that we're talking about, because the usual kind of program effectiveness research was developed in the non-COVID world. So I would urge you who live in the COVID world and want to do that research to just think about ways that you can gather data of the sort I have talked about in this new context. I don't have any real answer to that question. I'm going to go to the second question, which is, what is the difference between an interrupted time series and a regression discontinuity study? So I didn't discuss regression discontinuity studies in today's lecture. I probably should have, but I didn't, and I'll tell you why. I've been an education researcher for more than 40 years, and I cannot think of an intervention that I have seen either in policy or in sort of intervention programming that actually is suitable to the use of a regression discontinuity study. So a regression discontinuity study will do this just briefly, and you can look this up for those of you who want to see this. There is in a regression discontinuity study, there is a known assignment mechanism, a known mechanism assigning individuals to the treatment. Let's say for schools, for example, that any school which is above a certain index on the percentage of students in poverty gets assigned to the treatment, and any school which is below that cut point is not assigned. Okay, that's the definitive assignment to treatment, is known and used rigorously. So we have a cut point. That's the discontinuity point, the cut point for assignment to treatment. Now let's assume that the outcome of interest is student achievement. And what we're looking at is, we know that student achievement varies by the school's average achievement will vary by the percentage of students in poverty. And so as the percentage of students in poverty goes up, the average achievement level will go down. Okay, and so we can plot the data that shows that regression line. So now we have a regression line. Now the horizontal axis of that regression is percentage of students in poverty, and we throw through that horizontal axis the cut point. Okay, now you see what you've got is a regression line with a cut point, and it's sort of a declining. The regression discontinuity study hypothesizes that there will be a uniform difference, a sort of new intercept in that regression line exactly at the cut point, so that there'll be a discontinuity in that regression line right at the cut point where treatment is applied. And that's where you identify the program effect. Okay, so you can do that with cross-sectional data. An interrupted time series or a comparative interrupted time series, either one, looks at data before and after an intervention is applied, but it doesn't have firm rules about where that, who's getting the treatment and who isn't getting the treatment. And because of that, the assignment mechanism is unknown, and you have this problem that those who get the treatment and those who don't might have been unequal in some way. But the divergence here is one across time, not across some regression line. And so that's the main difference between a regression discontinuity, where you are throwing a treatment line through an existing regression of some variable and its outcome, versus some divergence at a discontinuity point that is a time point in the regression, in the interrupted time series. Okay, so I hope that answers your question, but I think you should really go read up on regression discontinuity if you want to do a regression discontinuity study. They are highly prized and well worth doing if and only if that cut point is rigorously enforced in practice. Because if you don't have a clear cut point, you can't do the regression discontinuity design. Okay. Here's Wilma Lynn asks me to discuss a research scenario. Let us read it together. The effectiveness of a flipped classroom was executed to diverse learners using the subject area in math. The researcher used a single pre-post design plus interviews using survey questions. Okay. Can we consider it a multiple design, and how do we deal with the limitations? if the respondents were randomly picked at pre-treatment and after post-treatment, do we solve any problems? Okay, so right, the normal. Okay, so the way that I discussed. There's two ways to do a pre-post design. Okay, one is to use the same subjects. I mean, in fact, and study only treated units, pre and post. And as I said, when you do that and you show a gain over time, you really can't rule out maturation, especially if learning is the outcome and you're giving the same test to kids twice. It's just almost impossible to say, well, it was the treatment that caused the learning. You don't have any data to rule out that it was just the kids naturally grow and learn. And you may have given the same test twice, which I do guarantee you does give the kids a better chance of scoring high. So that's the problem with the treated only. And you can do interviews and everything, but you can never really rule that problem out. So to rule that problem out, you add a control group in this pre-post design. And what that helps you do is say, well, okay, yeah, I've got maturation in history going on, but it's going on equally in treatment and control group. And so I can still now look at the difference in outcomes post-treatment or the gain in outcomes pre to post and compare that across treatment and control in an effort to identify a treatment effect. That design where there's an actual control group is a whole lot better than the one where there isn't in ruling out maturation in history, but it doesn't rule out the non-equivalence of groups problem. And so, and adding interviews and so forth is always helpful in trying to understand the context in which the design was implemented or the study was implemented, and understanding how kids reacted to it. But you have these problems in these designs, and there are trade-offs to the designs. But I personally think in a simple pre-post design, the addition of a treatment and control group is always better than just using a treated only design. So I hope that answers that question. So do action research and classroom practice and issues fall into the interrupted time series design is a question being asked. And what if there's a negative time trend after the intervention? And do action research qualified for the assumption mentioned in the given research design? So action research, I would argue, it depends on how you think about action research. One way to think about action research is as single subject design. I'm studying my own practice. I'm going to watch what happens when I do it. Then, yes, you can use the interrupted time series design in action research. That is, study my practice, gather some data on outcomes before I do what I'm focusing on taking action over, take that action and study outcomes again. You can do that. You could do that in a multi-site case study with colleagues. You could do that in a treatment and control condition. The thing is, what you don't want to do in action research, I think, is the sort of treated only, post-test only kind of reasoning where you say, I did this, look at how successful my kids are. That doesn't give you a lot of basis for showing that your actions were the cause of your kids' success. And so when you're doing action research, I find these guidelines for research design to be useful. They can help you guide your reasoning about how to conduct action research. And yes, I would argue that when you do action research, you should think along the lines of potential outcomes and use the potential outcomes framework to help you think about the evidence you've gathered and how you're going to go about gathering evidence. So I see no disjunction between action research and the kinds of research designs that I'm talking about. Now I'm moving to a question that says, in the multiple baseline design, is the lone treatment group divided into different subgroups that each will account for a baseline? Is it similar to having one or more control groups then? No, the point is the same. So we're going to do the multiple baseline. We're going to do it with only treated subjects. We're going to watch what happens to those subjects, and we're measuring multiple baseline measures. So the answer is no, this is not like there's a one group that gets this and another group gets the next one and another group. The same group of people are measured on all of the outcomes of interest at every time point in the study, and they get each treatment sequentially. So it's a, you can do them. I mean, the multiple baseline study with a control group would have a group that was watched during the entire time period where the baseline measures were collected, but none of the treatments that were of focal interest were administered. So I hope that helps you. I hope that helps you understand the question that you asked. I seem to have lost where I am. Let me see. I'm scrolling through here. Sorry about scrolling through here, but got to try to get back. Okay, I got the multiple baseline. So I'm going to the next question, which is, to introduce or add separate control groups, what are the possible characteristics that have to be addressed? Well, again, in my view, control groups should be selected from reasonably the same settings as are the treatment group. They should probably be of roughly the same age. Those will rule out kind of history differences. Does it make a lot of sense to compare an intervention done in Malaysia to a control group from Saudi Arabia? I mean, it doesn't to me. In a quasi experiment, that doesn't make any sense to me at all. If it was random assignment, well, then we would have mixes of kids from Malaysia and Saudi Arabia in both groups. Okay, so control groups in random assignment are always equivalent to treatment groups in the study. The problem in selecting control groups is when you're doing these matching studies or in naturally occurring group formation processes, and that's where you need to be attentive to comparing apples to apples, not apples to oranges, because we can measure all kinds of pre-treatment covariates on kids from Saudi Arabia and kids from Malaysia, but who's going to claim those kids are reasonably the same, even though I've measured all these covariates? So I hope that helps you understand that. What statistical tests do you recommend for the time series design? There's a bunch of ways to look at time series data. It can be quite complex, and I'm pretty sure, included in the back of the back slides of my presentation, a place you can go to find some relevant sources about that. If not, you just Google time series design. You'll find people who are talking about the various methodological strategies for using it. Time series design is in general more complex than cross-sectional or taking simple averages. But there are, anyway, it's a long question, and I said I wouldn't bog myself down, and then so I just, that's a place for further study. Then there's the question, do we sample first and then randomize? Yes, we sample first and then randomize. That way, we assure that we've got sort of, I suppose we could randomize first from the list, the sampling frame, and then try to choose from within it. But most people first sample and then randomly assign. So that's the answer to those two questions. Okay, this is a question again about random assignment and purposeful sampling. So it is the case that any intervention program is usually, in its early stages, not functioning in a completely representative set of contexts. So for example, a lot of interventions I study, for a variety of reasons, end up being located mostly in high poverty settings. So in a quasi experiment, I end up trying to match those to other high poverty schools. That's in the quasi experiment. Now, if I am going to do a random assignment study, I face the following question. First of all, I'm not going to study units that have already adopted the treatment because they would not have been randomly assigned. I'm going to study units that are going to adopt the intervention as part of the study. So I have to ask myself, do I want those units to be like the units where the intervention currently operates? In which case, I intend for my study to generalize only to that population of schools. Or am I going to try to see if this intervention works beyond the population where it currently operates, in which case I'm going to sample potential participants from a broader population. So it's very important when you design a randomized field trial to make decisions up front about which population you wish to generalize to. Not all interventions are meant to function with all populations, right? Some are meant to function only with a certain population. So when you go to choose subjects for a random assignment study, you may want only those kind of units to sample from. On the other hand, some interventions are meant to function everywhere, in which case, if you really want to demonstrate that the thing scales and generalize your results to where it's going to potentially scale, then you'll want to choose a population. You'll want to define your population much more broadly. Okay, I hope that answers that one. It says, even with randomization, the study groups can eventually be affected by differential attrition, I assume. Is there any way to control for or prevent this either in design or analysis? That's a great question. The premise of this question, which is even with randomization, there can eventually be differential attrition. Absolutely. In any study, differential attrition, which is, some kinds of people leave the study, that's a missing data problem, and then differential attrition, and they can leave at different rates, and then there's selective attrition, which is some kinds of people are particularly likely to leave one group versus the other, which can introduce additional bias. So to get at just the simple attrition problem, that is, people quit the study. It happens, okay? In any good study, the first thing you try to do is incentivize people who want to quit to stay in the study. But, we're under human subjects obligations. We can't force anybody who was initially in the study to stay in the study. So the next step is to say, okay, like here's an example. You have a school. it begins in the treatment condition. And you're running a longitudinal study. So 2 years into it, this school says, you know what, we hate this intervention and we quit. Okay, that's attrition. That's the attrition problem. What can you do about it? Okay, well, first you say, well, gee, you know, is there something I can do for you that would incentivize you to stay? If you can't do that, now you're stuck with dealing with attrition. One thing you can do that will help you at later stages in analysis is try to continue gathering at least some data, perhaps on the outcomes, even though the unit has engaged in attrition. If the unit does drop out of the study, it is often our procedure to drop its matched control also out of the study. Okay, so we do that, especially because we often match before we randomly assign. But the main point of this is, and I will discuss this in the final lecture when you get to the requirements for reporting on your studies, it's very important to report on attrition and differential attrition. And there are conditions of attrition when attrition is both large and affecting the treatment and control groups differentially, that you just have to say, I don't have trustworthy data. But differential attrition is really hard, and you have to work hard as an investigator to try to persuade and incentivize subjects to stay in the study as much as you can. So the next is, I know that randomization can only work if the sample size is large enough. In larger random assignments, how large is large? Well, it's the law of large numbers, right? Your chances of meeting the independence assumption go up as sample size goes up. There's no, luck of the draw, 2 could be large enough. A sample size of 2 in the treatment and 2 in the control. I mean, by random chance, randomization could work out. On the other hand, it might not work out. And the same would go for like 50. So the point of this is not that, to force you, to burden you with having to choose an extremely large sample. The idea is to simply check after you've done randomization to make sure that the assumptions of random assignment about equal distributions on pretreatment covariates has been met. And, you can tolerate small failures or perhaps introduce controls, statistical controls into your models in light of that. In general, and I will talk about this in the next lecture, people think about sample size for these kinds of studies is by looking at statistical power. When do you have enough sample size to be able to actually detect small effects as statistically significant? And so, in group randomized studies, the general answer is 25 cases in treatment and 25 in control. That's a general kind of rule of thumb that I would say. But by chance, you can have failures of randomization with that number. So it doesn't guarantee, it only works in expectation, but it's the best tool you have to attempt to assure that not only the observed, but the unobserved variables are controlled for. And that's why people use it, even though it can fail. This is a question that says, I'm using a quasi-experimental design for my research. Is cluster sampling appropriate? So I'm assuming that by cluster sampling, one means that one is sampling clusters of observations, and that those clusters are the unit of treatment. So let's assume that a cluster that is being sampled is a school. So like I'm really interested in the effects of the intervention on kids' achievement, but it turns out that the kids are clustered within schools. So I select schools to get at the kids, and then within the schools, I sample kids. So if that's your design, what you match on is school characteristics. And you study the treatment effect as if the treatment effect occurred at the school level, and you use a multi-level model where the outcome is at the first level and the treatment effect is estimated at the second level. I assume you are not thinking about doing an assignment where you select schools and then choose to study students within schools that have either been treated or not treated. But then you know, what you're doing is matching the kids within the clusters on characteristics and using either fixed or random effects to take care of the clustering. It's a complex question, but I hope that that helps address your question about cluster sampling. You know, I said this the last time, the clustering of observations within schools and education research adds an additional layer to this research design literature that often isn't talked about in the general literature. And I'm struggling to think about the extent to which I need to cover that next time when we talk about thinking about what kind of effects we're estimating. I'm leaning towards spending some time talking about clustering. But I hope that helped to address that question. Yeah, this is the question again. It says, at this time of pandemic, how can we conduct our research effectively knowing that there's no physical interaction? I don't have an answer to that. I will confess to you, colleagues, that I have turned down doing research, not only because I'm retired, but because the pandemic makes it so difficult. So I wish you all good luck in trying to figure this out, and would think that you have more expertise or will develop more expertise in it than I ever will, because I spent my life as a pre-pandemic researcher. And this next one is also the new normal. What's the best design? Again, the best design is to fit to the circumstances of questions you're asking and resources you have. The next question is, what are the considerations in terms of the DID model to avoid biases on time trends? And should we use it in control and treatment groups? Well, so the difference in difference design always has a treatment and a control group, right? And that always has those two time trends being examined pre and post treatment, with the expectation that the time trends are equal in the first time period. And so the main consideration in choosing the difference in difference design or proceeding with that design is, first of all, that those time trends are equal. And you know, you can test that statistically, so that's not a problem. The next assumption, which is that because they're equal, I have sort of controlled for all kinds of pre-treatment X's that are affecting that. And so when I observe post-treatment, the only thing that could be making a difference in the trends I'm observing is the treatment. That's a strong one. Okay. And, you know, you can show that they're alike on observables, but you can't prove that they're alike on unobservables. And that's just, you know, that's the same for any design short of random assignment. Okay, so that's my answer to that one. We're going to go on. I'll take a few more questions. If you're interested in leaving at this point, I certainly understand that. Is it here's a question that's in, is it possible that the pretest outcome is higher than that of the post outcome? And if yes, what do you think might be going on? And thanks so much for your response. Well, I mean, in education, we like to think that, like learning is the outcome, and boy, we sure hope it goes up over time, right? But you can think of lots of outcomes or lots of treatments in which you hope that the value of the outcome variable, in fact, goes down over time. So I'm in a school. I wish to decrease the incidence of bullying. That's one where I hope that the post test is lower than the pre-test. And you can think of all kinds of cases in which you want that to happen. Um, so in fact, then what you're looking for is a tau average that's negative in value. You want to see a decrease. Okay, so yeah, I mean, tau average doesn't, the direction of tau average is you're hypothesizing that. Sometimes you want the tau average to be positive, that is, things to go up over time. But sometimes your intervention is to have things go down over time. That's okay too. So that's the answer to that one. This question is, how can we know that our subjects are enough for being good evidence? I think this must be, there's two ways I'm interpreting this question. One is it's just a sheer sample size question. That is a, and so there's a lot of ways to think about that one. So let me work through this. If you are studying a single subject, as a clinician, you're trying to understand, what can I do with this child to change this child's outcomes? I'm going to do a single subject's research design. I will observe the child for a number of occasions, intervene, observe. Okay. The answer to that is, I know I sort of begin to trust my results when I've built up enough time points of observation on a single subject. But in this case, right, I'm only trying to figure out whether what I'm doing is valid for that single subject. Now, suppose I want to ask, well, if I do that treatment with a subject, does it generalize to other subjects? Now I face two problems. One is, how large does my sample need to be, and what does it need to look like to generalize beyond my subjects? And that's the question of, you shouldn't probably generalize beyond the types of people in your study. And the second question is, how large does my sample need to be before the results that I am observing are stable? Just think about the law of large numbers. The more observations that I accumulate over time, or the more subjects that I include in my study, the more precise is my estimate of tau average. So that's, you can look at like sample size calculators to get a sense of what kind of precision you're going to get on a given measure, given that measure has certain properties, or on a given statistic. So that's really the notion here about how do I mean, that's my answer to that question. Trying to give a concrete research where counterfactual design was used. Well, I don't know if that means, like, a concrete example would be, I am studying an intervention called Success for All, and I can do this in any number of ways. First of all, I can study only schools that were in Success for All, and I can study them after they were in Success for All. I can take a single pretest of the achievement of kids before they were in Success for All and after they were in Success for All. Or I could study the achievement of many cohorts of kids in those schools before they entered the treatment of Success for All, and then afterwards. Or I could study a bunch of schools that were in success for all, comparing them to a bunch of schools that were not in success for all. That's the treatment and control comparison. I could try to match the two groups, or I could randomly assign. So that's the counterfactual design, and that's an explicit example of how that would be used. That's as concrete as I guess we need to get. How does the counterfactual design differ from a causal comparative design? So these are terms of art. I'm not sure what you mean by the causal comparative design. I think there's a textbook that uses that term, but the counterfactual, my thinking is that sometimes causal comparative designs are simply thought of as correlational designs. That is, the correlation, you're looking at multiple units with different values on an independent variable and correlating those values to some other variable, the outcome, let's say. You could think of those as causal comparative, but as we discussed, because you're comparing units with different values, but as we discussed, these are correlational designs, and so they can't handle the problem of causal ordering or spurious correlation, and so the counterfactual design has a bunch of ways of doing that and studies treated and untreated groups, not groups that have different values on an independent variable, or put differently, the only independent variable is treatment yes or no. Okay, so that's kind of the difference. I would think that, under some circumstances, the counterfactual design is a form of causal comparative design. In choosing a control group, if we cannot find a good match with the treatment group through random assignment, means we can select them purposively. So first of all, you have a group of cases that are potentially going to participate in your study. In random assignment, you take that group and randomly assign them to treatment or control. Okay, so there's no matching going on. You're just thinking that, if I randomly assign this group, I'm going to get group equivalence at the end of the random assignment. Now, I can match before I randomly assign, and that does have the danger that if I can't find a match for a particular case, then I don't include that case in the study. And then there is no purposive selection in random assignment, except the purposive selection of schools that are in the pool to be randomly assigned. They can be purposively selected. If purposively means from within different strata or different geographical regions, not randomly sampled from the population of all schools. Okay, so you can purposively create the pool to be randomly assigned and then randomly assign or randomly assign after matching. This question asks, I suppose, is there some sample selection technique that results in reliable research results? Well, rather than talk about reliable research results, I think that the research community generally talks in terms of internal and external validity. Internal validity is the strength of the causal inference, and in our case, the extent to which your method has really made you reasonably confident that you've met the independence assumption of the potential outcomes framework. That's independent of sample selection. And so, internal validity doesn't have a lot to do with sample selection. External validity is the extent to which you can generalize the results from your study to some inference population. And that's where sampling comes in. You know, if you say, I wish to generalize the findings of my study to schools that serve a lot of poor children, but your study was only done in schools that serve a lot of rich children, you have probably failed the external validity test. So, okay, it's not reliable. It's think in terms of internal and external validity. And finally, what is the basic difference between instrumental variables and panel data analysis? And will it work for data without baseline and without control? You know, IV is used in all kinds of circumstances, panel data, not panel data, well-defined treatment groups, or, treatment groups that are defined on some continuous variable. Again, I would urge you to go and consult the literature on instrumental variables because, it's quite complex, been used forever by economists, so they have lots of techniques for lots of different kinds of data. So it looks to me now like I have come to the end of answering the questions, and I thank those of you who have stayed with us for the entire time. Thank you for listening to me. Thank you for addressing these interesting questions to me, and I look forward to seeing you again. So with that, I'm going to turn it back to our moderator. So goodbye, everyone. I will see you next time.